Curves in industrial design. C2 condition and polar form of the Bezier pieces of a B-spline curve. The control polygon of a cubic Bezier curve parameterized by T between U and V can be given in terms of the polar form of the curve. The first control vertex is the polar form evaluated at U 3 times, where U is the left end of the time interval. The second control vertex, C1, is obtained by evaluating the polar form at U twice and V once, where V is the right end of the time interval. We can keep going with the rest of the points of the control polygon each time we evaluate the polar form at U 1 time less and V 1 time more. For example, the third vertex of the control polygon is the polar form evaluated at U once and V twice, and the last vertex of the control polygon is the polar form evaluated at V 3 times. Here we have two Bezier curves, the first one in red with its control polygon, which is a cubic Bezier curve, and the second one also a cubic Bezier curve in green with its control polygon. If the first Bezier curve is parameterized by T between U0 and U1, its control polygon can be given in terms of a polar form of the curve, and the first vertex of the control polygon is the polar form of this curve evaluated at U0 3 times, because U0 is the left end of the time interval. We get all the control points of the curve by evaluating the polar form. In the same way, we can do the same with the green curve. If C2 is the polar form of the green curve, which is a curve parameterized by T between U1 and U2, its first vertex is given by its polar form, the polar form of the second curve, evaluated at U1, where U1 is the left end of the time interval. The union of two cubic Bezier pieces, the first one C1 parameterized by U0, U1, and the second one C2 parameterized by U1, U2, is continuous at the join if the last vertex of the control polygon of the first curve is equal to the first vertex of the control polygon of the second curve. That means that the polar form of the first curve evaluated at U1 3 times and the polar form of the second curve evaluated at U1 3 times are equal, and in fact they are equal to the control vertex C3. Here we can see the control polygon in terms of the polar form of the first curve and the control polygon in terms of the polar form of the second curve. We see that the union is continuous if this point is equal to this point, which are the two polar forms evaluated at U1 3 times. So we've been able to give the continuity condition in terms of the polar form, being that the two polar forms of the two curves are equal evaluated at the time of the joint. Now we are going to try to do the same thing with the C1 condition. The C1 condition is a condition that involves this point, and this point. This curve is a continuous curve, but it's not smooth. It has a corner at the joint of the red curve and the green curve. So by moving the slider, we are going to smooth it out, and this is now a union that is a smooth curve. We see that the condition of being smooth is a condition of these 3 points being collinear and also in certain proportion. We are going to see how we can write this condition in terms of the polar form. So let's go to the initial position. So as we said, the C1 condition depends on these 2 points. So we are going to consider the line that passes through these 2 points. And also it involves these other 2 points, and we are going to see the line that passes through these 2 points. These are the lines in green and the line in red. So the parameterizations of these lines can be given in terms of the polar form. The line in red is the polar form of the first curve evaluated at U1 twice and a free parameter t. And the line in green is the polar form of the second curve when fixing U1 twice and leaving the third parameter free as t. So when we move the slider to get a C1 curve, we see that these 2 lines coincide in fact. So we're going to see exactly what it means in terms of the polar form. So now consider these 2 points, the green one and the red one. The green point is a point on the green line that is obtained by choosing certain proportion given by the time parameters u0 on the green line. So it's the point of the polar form of the second curve evaluated at u0, u1 twice. And the red point is also a point on the red line that is obtained at a certain proportion that depends on the time intervals. So in this case, the time chosen, the value for the parameter t, is u2. When we move these points, in order to get a smooth curve, we see that these points approach and finally get to be equal to the polar form of the other curve. In particular, it means that the polar form of the first and second curves are equal when evaluated at the points u0, u1 twice, and evaluated at the points u2, u1 twice. So the union of two cubic Bezier pieces, the first one C1 parameterized by u0, u1, and the second C2 by u1, u2, has continuous derivative at its joint if the polar form of the first and second curve are equal when evaluated at u1 twice and u0 once. And in fact, this is the third point of the control polygon of the first curve. And also, the two polar forms are equal when evaluated at u1 twice and u2. And in fact, this point is equal to the second point in the control polygon of the second curve. The reason is that the C1 condition means that these points are in a combination, and in fact they are an affine combination. Because C3 can be given in terms of the polar form of the first curve, and also C2 can be given in terms of the polar form of the first curve, we can solve in the affine combination for C4 and write C4 in terms of the polar form of the first curve in this way. We can do the same thing, but this time solving for C2. When we solve for C2, we write C2 as an affine combination of C3 and C4, which depends on the polar form of the second curve. And when solving, we can see that C2 can be given in terms of the polar form of the second curve in this way. So this is the C1 condition in terms of the polar form. In general, even when we have a C1 union of two curves, we've seen that this line is the same line written in terms of the one polar form or the second polar form. In fact, when we fix the parameter u1 twice in both polar forms, we obtain the same parameterization of the line. The C2 condition was a condition in terms of these two vectors, that they have to be both parallel and given in certain proportions, and the proportions are given by the time intervals. In this case, this curve is a C1 curve, but it's not C2 because the two vectors are not parallel. What it means in terms of the polar form? When we consider the line passing through these 2 points, and this point, which is a point on that line given at time u2, and the line passing through these 2 points, and this point, which is the point given on this line at time u0, and these are the parametrizations in both cases given by polar forms, we see that in general these 2 points do not coincide. In fact, when the curve is a special curve, it is in the space, the two lines may not even intersect. So we are going to see what this means in terms, the C2 condition, what it means in terms of the polar form. On the screen we can see C1 union of two cubic Bezier curves, and it's not a C2 union because this vector and this vector are not parallel. So when we move the slider to get a C2 union, now the resulting curve is a C2 union of two cubic Bezier curves. This vector and this vector are both parallel and are in the proportion given by time parameters. So this is the C2 condition. So we are going to see how we can write the C2 condition in terms of the polar forms. So consider the two polar points we mentioned before. the one on the line that passes through these 2 points, which is the line with parametration, the polar form evaluated at u0, u1, and a free parameter t, and the point is obtained when the free parameter is u2. And also this line, which can be parameterized by the polar form of the second curve, evaluated at u1, u2, and a free parameter. This point is obtained when that free parameter is substituted by u0. In general, in a general situation where the union is not C2, these 2 points are different. But when we get a C2 curve, these 2 points coincide. So the condition of being C2 means that the polar form of the first and second curves are equal when evaluated at u0, u1, u2. So in summary, for a cubic B-spline composed of 2 Bezier pieces, the first one C1 defined on u0, u1, and the second C2 defined on u1, u2, the continuity condition means that the polar form of the first curve and the polar form of the second curve are equal when evaluated at u1 3 times. The C1 condition is equivalent to saying that both polar forms, the one given by the first curve and the second curve, are equal when evaluated at u1 twice and u0, or when evaluated at u1 twice and u2. That means that this line, the lines defined by the polar forms with u1 fixed twice and t free parameter, are the same parameterization. Finally, the continuity condition of the curvature, the condition of being C2, is equivalent to saying that the 2 polar forms are equal when evaluated at u0, u1, u2.